Alright, welcome back. So let's look into the first example. So the rabbit's ears can be either short or floppy, where short ears are dominant over the floppy ears. So there are 653 rabbits in that population. 104 rabbits have floppy ears and 549 have short ears. The next generation of rabbits has 560 individuals with short ears and 840 individuals with floppy ears. So is this population in hardy-weinberg equilibrium? Right. Again, first find the frequency of dominant and recessive alleles and the frequency of the individual with dominant, heterozygous and recessive genotype of the generation yang dia dah state. So now in this question, look carefully. There are two generations. First, the generation, this is generation number 1, and then we have the second generation, which is this generation. Excuse this. Okay, and then we have the second generation. So you have two sets of information. You have the generation 1 and you have the generation 2, right? Now, so generation 1, kita ada total 653 rabbits. And then floppy ears, short ears are dominant. So floppy ears, they are homozygous recessive. So Q squared is 104. Remember, 549 is not P squared. Okay, it's not. So don't start with the dominant numbers, rabbits or individuals of that question. Always start dengan recessive. Okay, baca soalan betul-betul. Rabbit ears can be either short or floppy. Short are dominant over floppy ears. So floppy ears, they are recessive. So how many floppy rabbits in this first generation? It's 104. So Q squared is 104. So is 104 homozygous recessive rabbits. So bahagi dengan 653. So what do you get? You get 1593. Right? So that is Q squared. You want to find Q. So you have to square root this number. So you get 0.399-ish, which is kind of close to 0.4. Right? So this is your Q. Now, what is your P? 1 minus 0.4, 0.6. So now you have to calculate P squared, which is 0.6 square, and then you get 0.36, and then you have to calculate 2PQ, which is 2 times 0.6 times 0.4, which will give you 0.48. Now, so you have this information of this first generation. I'm going to put it here. Okay, what you have to find is P squared, 2PQ, and Q squared. So this is the first generation, and then this is the second generation. So you know that P squared is 0.36, 2PQ is 0.48, and Q squared is, where are you? Q squared ni Q squared yang ni tau. Yang ni adalah 0.4, 0.16. Okay, now you have to calculate the second generation pula. You do the same steps. Okay, I'm gonna erase this part. Generation, now we are calculating the second generation. Bear with me, guys. Okay. Alright. Now, second generation. Okay, so this is second generation now. There are 560 rabbits. So somehow the number of the members in that population dah decrease. Okay, tadi 653, now is 560. Again, you have to find Q squared. Homozygous recessive rabbit would be 840. Okay, 840 over how is this possible? Kejap 560 individuals. Sorry, my bad. The next generation have 560 individuals with short ears and 840 with floppy ears. So 560 plus 840. Okay, this is the total rabbit in that population. Sorry, my mistakes for not reading questions carefully. So please read your questions slowly and carefully and understand it. So there are 1,400 rabbits in that population. So the number has increased from 653 rabbits from the first generation to 1,400 rabbits in the second generation. So homozygous recessive is 840 rabbits over 1,400 rabbits. You will get 0.6, right? So Q squared is 0.6. So Q is a square root of 0.6. Oopsie. Which is 0.7746. So P is 1 minus 0.7746, which is 0.2254. Now, what is P squared? It's 0.051. Now, guys, Q squared, tak nampak square dia kat sini. Okay, Q squared is 0.6. Kita tengok allele frequency dulu sorry, bukan. Kita tengok ni. P squared is 0.051. Q squared is 0.6. Sama ke tak sama? P squared of the first generation is 0.36. The second generation is actually lower, 0.051. But then again, Q squared for the first generation is 0.16, and then the second generation actually gives you a 0.6 value for Q squared. If you look into this just number and without actually calculating the 2PQ of the heterozygous number for the second generation, the value has changed. Okay, the value has changed. So the value has changed. So this means the answer to this question is no. The population is not at hardy-weinberg equilibrium because the homozygous because the genotype frequency for the dominant for homozygous dominant has changed because all the frequencies have changed. Basically, all the frequency have changed. Now, the question can also ask you how the mechanism of changes. Contoh macam, does it increase, does it decrease, macam tu. So if you look into this part, for example, so now you know the frequency for homozygous dominant actually decrease, while for the frequency for homozygous recessive increase. Okay. So tengok soalan, kalau dia suruh describe, you describe. Kalau dia tak suruh describe, so you jawab je no. No, there is not at hardy-weinberg equilibrium because all the frequencies have changed. Now, let's look into the second example. So, in a sample of mushroom from a forest floor, 3 genotypes are controlled by 2 alleles, big A and small a, at one locus, showed the following numbers in the population. Homozygous dominant, there are 15 of them. Heterozygous ada 80. The homozygous recessive ada 5. So, are this number, what would you expect if this population was in hardy-weinberg equilibrium? Now, so how do we answer this? Again, find the frequency of dominant and recessive allele and the frequency of individual with dominant, heterozygous and recessive genotypes. Before we proceed with the second example kan, yang ni, this one kira must calculate also. Because I'm afraid that in dalam skema jawapan ada markah untuk benda ni, right? We never know, so just calculate them. Right. Now, okay, so how do we start with this question? So, okay, for this population of mushroom, you have to calculate the number of total mushroom in that population first. So, always start with something that you can figure, right? Kalau you blur, so 15 plus 80 plus 5, which give you 100. 15 campur 5, 20. 20 campur 80, 100. Okay, so we have a total of 100 mushroom. So you have to find P and Q first. And then of course, kena start dengan Q lah. So Q is 5. So Q squared is 5 over 100, which is 0.05. Right? So Q is the square root of 0.05, which is 0.2237. Please don't be afraid when you get this kind of number. Just yakin je lah. Okay, yang penting you start dengan Q. So Q squared is 5 over 100, which is 0.05. So this will give you Q, a square root of 0.05, which will give you 0.2237. Now, what is P? P would be 1 minus 0.2237, which is 1 minus 0.2237, 0.7763. So now you know P and you already know Q, right? So now you use this value, P and Q, compute these values into P squared plus 2PQ plus Q squared. So this is the observed calculation. So this is the observed information given. So you now have to calculate the expected number or values. So you have to compute P and Q into P squared plus 2PQ plus Q squared. Right? So let's do P squared first. P squared is 0.7763 squared. So you get 0.603 kinda. And then Q squared you already know lah, 0.05. Now what's left is 2PQ. 2 times 0.2237 times 0.7763, which is, let's calculate that, 2 kali 0.2237 kali 0.7763. So you'll get 0.3473. So what do we do with this number? So what you can do is that, so let's say Q squared is 0.05, right? Kita ada 100 kan? So you times it by 100, the number of members in that population. Bukan percentage ni, ni number of population. So you get 5. So ada 5. What about P squared, which is 0.7763 times 100? So you get about 77.6, kind of like 78, right? Mushroom. And then you have 2PQ. 0.3473 times 100 gives you 34.7. So you have like 35 mushroom. Now, so from the expected calculation, from the expected values, yeah, you just calculated, homozygous dominant is actually 78. Excuse kejap sorry guys, my mistake again. Not 0.7763, is actually 0.603. 0.603, so this should be 60ish. Okay, not 78, 60. Homozygous recessive would be 5, maintain sama and then heterozygous is 35. So 35 plus 5, 40, 40 plus 60, 100. Why I stopped just now is because I was adding up this value 78 plus 5 plus 35 in my mind, and then it's not equal to 100, and it's wrong. So bila you calculate number of population, mestilah lebih kurang je. Okay, 100. So 35 campur 5, 40 campur 60, 100. Ini untuk expected population So number of members in that population kena sama. Dia tak sama macam soalan yang sebelum ni. Yang ni dia dah bagi tahu memang ada perubahan pada members in that population. Yang ni untuk soalan ni dia tak bagi tahu sebab dia suruh predict saja. So bila kita predict, kita kena kekalkan number of members in that population. So all you have to do is to find P and Q and compute dia dalam hardy-weinberg equation ni. So and then you calculate, dah dapat P, dah dapat Q, kira P squared, kira Q squared, which you dah kira dah sebenarnya, and then 2PQ, and then you kena darabkan dengan number of members in that population, which in this case is 100. So bila you darabkan, you dapat 5 untuk Q squared. So 5 memang tak berubah. So you comparekan dia, yang observe dengan yang you calculated. So 5 dengan 5 memang tak berubah. But then again, untuk heterozygous you dapat 35, but then the observe is 80, so berubah. Ni sama, ni tak berubah, ni berubah. And then also when you calculate P square, you dapat 60, and then but the observed value is 15 and not 60, so ini also berubah. So this is also not at equilibrium, hardy-weinberg equilibrium, because the expected values change or not, it is significantly different than the observed value, sebab terlampau beza. Melainkan if this question is 15 and then you actually get around 16, and this one you get 79, and then this get macam 5 juga maybe. And then kalau perubahan yang kecil macam ni, kita boleh kata negligible lah, but kita boleh cakap dia lebih kurang, and then it's still at equilibrium. But in this case, terlampau jauh perbezaan dia, so it's not at equilibrium. So this brings you back to this slide. Okay, this second part. This is the second part. Observe and expected, they are significantly different. Memang terlampau jauh berbeza, so the population is not in equilibrium. The first one, early frequencies change. So ini merujuk kepada this first question where you are given with the information of both generation 1 and 2, and you have to compare them. Okay. Untuk second generation is where you have to actually calculate the expected and compare with the observed. Observed mean the ones given by the question. Right, so that's all about determining the equilibrium, the equilibrity of a population.